Let's now take a shift, and we're going to shift from going to the kinematic world to going to the kinetic world, or the cause of motion. And we're going to begin just like we did with kinematics, and we're going to begin with the linear components, and then we'll go further from there. But to basically understand the idea of how objects interact with their environments, we're going to really look at the physical interaction, and we're going to do this through the concept of force. And it goes back to Isaac Newton and the apple falling from the tree, and you talk about gravity, but that's what this image is all about here. But to do this, we're going to start really by identifying the cause of motion, and that's that branch of mechanics that deals with kinetics. And so within kinetics, we identify the force. And to define a force, it's generally defined as either a push or a pull, and that's something that people have a hard time really understanding to begin with. But it could be a push or a pull. Remember, your muscles only pull, they don't push. But if I push on something, I'm applying a force as well. And it's a push or pull that tends to change whatever the current state of motion of the object is. And that object could be stationary, it could be moving, it could be accelerating, decelerating, it could be constant velocity, but this force tends to change that current state. And so these are some just images that I've taken from different sources that kind of identify the play and interaction of a force. Down here, what you see with these tug-of-wars is you see a few forces acting, and you'll understand more about a free body diagram later, but understand that all these red arrows represent some kind of force that's acting on the system, and we'll talk about what systems are and how to identify the system a little bit later. But understand that there's forces that are acting throughout the environment. They act in the vertical, they act in the horizontal, and so that's a really key component, is knowing that it's a push or a pull that tends, it doesn't always, but its object is designed to change the current state of motion. So now as we go forward, let's talk a little bit more about force and what the characteristics of force are. And there's three main characteristics that I want you to remember for our purposes. And that is that a force is a vector, so it's made of a magnitude and direction. It consists of a point of application, and then there's a line of application. And the line of application really goes along the lines with the vector, and you can see this depicted here on this image over here on the right. But here you have the vector, magnitude and direction, right? So the magnitude is the length of the line. The direction has a lot to do with this angle of application. But then again, what we have now is we have this concept of the line, and that goes along the line of here. So there is a line of where the force is being applied through this point of application. And in this situation where you have somebody standing on the ground, there's what we call a center of pressure, and that center of pressure identifies where the point of application of the body is in response. And generally the line of application and the direction of which it's going through tends to happen in the center of mass of the institution with the ground reaction force. But gravity always acts to going down from the center of mass, and so that would be the point of application, would be the center of mass of the system. So as we go forward, understanding this line of application is in the direction of the vector, and then it tends a lot to do with the magnitude of the vector of that line of application. But the point of application is where the force is acting on the system. And we'll talk a little bit more about that again with those free body diagrams and where to put that point of application and where that line of application, what direction it should be going. To understand the force a little bit more, let's understand that the unit of measurement is a Newton. And remember, if F equals ma, that means it's kilograms per meters per second squared. So the mass is kilogram, and then the A part is meters per second squared. So newtons are kilograms per meter squared. And so now, this is an image of the famous book, Principia, by Isaac Newton, where he describes his 3 laws of motion. Now, it's very important to understand too that these laws of motion are laws now and not theories, and they've been tried to be proven wrong, and they hold up to everything that's been thrown at it for years. But they are the law of inertia, law of acceleration, also known as the law of momentum, and the law of action-reaction. We're going to go into depth of understanding these. But what I need you to be able to do is understand Newton's first law, Newton's second law, Newton's third law, and be able to identify what those laws are. So Newton's first law is the law of inertia, Newton's second law is the law of acceleration, and Newton's third law is the law of action-reaction. So you should be able to recite those. And then take these further. Let's go. The law of inertia, which is his first law of motion, identifies an object's tendency to resist motion. And that is that objects tend to want to stay in their current state of motion, and they will unless they're acted on by an outside force. So let's describe what inertia is a little bit more, and that is it's a resistance to motion related to its mass of an object, right? So a heavier mass has a greater inertia. And it's a portion of matter that allows an object to remain in the current state. So just think about how easy it is to push an empty box versus as a rock or the box fills up with matter, how more difficult it is. Mass is a measurement of the amount of inertia. So when we measure something in kilograms, that is a measure of its inertia because the more mass or more amount of kilograms, the greater the inertia of the system. Therefore, it needs a greater force to move or change the current state of motion. So let's think about a windy day and the type of objects that are blown around first. Also think about the number of balloons that you would have to fill in order to lift you off the ground versus somebody like your niece or your nephew who's a little bit lighter. So when I think about this law in action, for sporting events, I often think about a sumo wrestler or other forms of physical combat sports. And there are typically weight classes because mass represents the difficulty in moving, the other due to that inertia. In sumo wrestling, it is difficult to get someone moving, but if you've ever seen a sumo wrestling, once somebody gets going, it's much more difficult for them to stop that motion. That's because of their great inertia or small inertia. It's much more difficult to change that current state of motion. Going on to Newton's second law, law of acceleration. Now, originally when Isaac Newton created this law, it was called the law of momentum. And we'll derive that equation for you in a moment here, but just understand that in our purposes, law of acceleration is fine is because of the way that we write the equation. If you took a classical mechanics class or a physics class, it may be written as a law of momentum. So either one in this case is going to be okay for our purposes, but understand that it's law of acceleration or law of momentum is Newton's second law. And what does that say? Well, it says that an object's acceleration is proportional and in the same direction of the resultant force, and it's inversely proportional to its mass. So if we look at the equation, we have it here. So it's the sum of forces acting on a system are equal to its mass, which is the measure of inertia, remember, and the acceleration, okay, which is the change in motion of the system. And so it's written as acceleration equals the sum of forces divided by the mass. And this is where you get is proportional to the resultant force and inversely proportional to the mass, is if we just rearrange it to isolate the acceleration components. Okay, so the sum of the forces on the left-hand side, or the cause of motion, equals the outcome on the right-hand side. So this is, here we have the causes, here we have the outcome of the forces. And that is how this equation is written. So Newton's second law, simply the more force, the more acceleration of the same mass. So as we increase the force on the system, if the mass remains the same, there should be an increase in acceleration on the system if it is a purely relationship model. Now we will talk about in a little bit some other instances throughout class where the human body can manipulate these in landing and some sorts of aspects. But understand for our purposes in a purely mechanical model, F equals ma, or the sum of the forces equals the mass times the change or in motion of the system. So looking at that cause and outcome a little bit better on the bottom here, we have F equals ma. So again, here we have the cause with the kinetic component, and then we have the outcome, which is a kinematic component. Now, if we look at this, the object of these two individuals, the mass, of course, is differently for these two objects. If they both want to have the same acceleration on their rocks, then the force will have to be different based on the mass or the inertia of the object. So if we put the blonde-haired kid as A and the brown-haired kid as B, which one would need to create a greater force or pull on the rock to elicit the same acceleration as the other one? And of course the answer is A. A, and you can see it from their images, A has to increase his application of force, or the amount of force, because the inertia is and quantified as mass of the object or rock he's trying to pull is greater. So as the mass increases, if we want the acceleration to remain the same, then we must increase our force. Vice versa, if the mass or inertia of the object is to remain the same, saying that both of these rocks are the same mass, and we want to increase the acceleration, we would also have to increase the force application. So this is how it all kind of relates to each other, and now we're using that. So let me take you back to what I talked about with the law of momentum and where this is, where it is derived from, and why it's now F equals ma. And so when Isaac Newton initially did it, he in rho is known for momentum. And if we take momentum a little further, momentum is mass times delta v. It's the motion of the object is essentially what we do. And so if we want to take the rate change of that, and we have F mel delta v, and we take that over delta t, hopefully by now, as I write that out, you can see where acceleration comes from. And so if I take this portion of F equals momentum over time, or the rate change of momentum, and take it further, it now becomes mass times acceleration, right? So if I do the sum of the forces equals sum of the forces causes the mass to change motion. Okay, and that A, or acceleration, is resulting of that mass and its change in velocity over time, which is the acceleration component. So this is how we have taken and derived the law of acceleration from the law of momentum and shown that they are exactly the same concept. Now, Newton's third law of motion, which is his law of action reactions, really identifies the interaction between two objects. And this interaction is when one object exerts a force onto another one, then it's going to get one that's equal and opposite exerted back onto itself. And so we'll just walk a little slower through that. So if I have two objects, A and B, for every force exerted by an object, there's going to be an equal and opposite force on that object. So the equation looks like this. For the sum of forces A on B, so the sum of the forces that A exerts onto B, B then exerts the equal and opposite forces back onto A, right? So every force exerted by A onto B, B then does an equal and opposite back onto A. So that is the key component here, is these two terms that I really want you to understand. B on A, by and on. The other important is equal and opposite, right? So they need to go in the opposite direction and they need to be equal. And we'll talk a little bit about this mostly when we get to ground reaction forces a lot, and then the interaction between objects. But for our purposes, a lot of the walking, running, jumping, as we get into the lab assignments, is going to be important for you to understand that when I do something on something, it's going to be back. So when you measure somebody's weight or the ground reaction forces from a force weight, you're actually measuring the second component of it. You're not measuring how much I'm exerting, or my mass is exerting on the object. We are actually measuring the equal and opposite of the ground back onto us. So we know how much the gravity and our mass are pushing down on the ground by the measuring how much is coming back towards us. So that's where we're really using this concept is when we're talking about ground reaction force, when we're talking about scales, when we're talking about measurements in a lab, we're often measuring the reaction to us interacting with the environment. And so here's what it looks like, right? So with that ground reaction force, here the person, the runner, pushes down on the ground, but we're not actually measuring that. What we see is this component here with the ground pushing back on us. And so whatever the magnitude of that ground reaction force is, just understand the individual itself is pushing the opposite direction. And you can see each of these ground reaction forces are resultants, and they're at an angle. And so again, we break it down into the vertical and horizontal. But again, and then if we look at the swimmer, oftentimes you'll see that sometimes they have a force spread on the wall, and you can measure the push off of the swimmer. But again, it's measured the wall on the feet, and whatever your positive direction is would be the measurement of equal and opposite. Now, the final component that of linear kinetics I want to talk about is what is actually represented of a object when we talk about linear kinetics. Because we already talked about human motion being a combination of rotational and translational, or linear and angular. And if we look at this depiction, there's a dot that is represented and right about here, and we call that the center of mass. And it's the center of mass of the object, right? And it's very important when we talk about linear kinetics in the measurement of ground reaction forces, in the measurement of where these forces are applied to an overall system or an object. They react and respond to the center of mass in a linear world. Okay, so that's very important for us to understand that in this linear world, the center of mass of the object is essential in determining where the force application is. So in the center of mass, and that is where the object tends to be centered. So if you hung it from a wire or hung it from a string, there would be no rotation because it would be perfectly balanced. Another topic that you'll come across is essentially the same thing, but it's the center of gravity. And all that's different between the center of gravity and the center of mass is the center of mass has an X, Y, and a Z delineation, or 3 orthogonal components. So it's in 3D motion, where the center of gravity only acts in the downward motion of the pull of gravity. So it's only with respect to gravity. So that's the vertical motion pulling you down towards the center of the earth. So this linear kinetics world, really important to understand that the application typically is with respect to the center of mass of the system, or wherever the point of application of the pressure is. And so we'll talk a little bit more about that in a little bit.